Hello everyone, I am P. Muhammad and this is the second session of thermodynamics. At first I want to tell you, memorize that when I say V, I mean actually V divided by N. This is the molar volume. I don't want to carry with me this N, and so I actually define V as the molar N. Okay, this session I want to talk about the zeroth law of thermodynamics. Consider three systems, 1, 2, 3, that are in equilibrium 2 by 2. I mean system 1 with 2 and 1 with 3 and 2 with 3 are in equilibrium. And remember that when we had two systems with a piston here that can move right or left, this piston will move right or left until the collections of particles here and here cancel each other and it reaches, for example, here an equilibrium state. So this can define actually in experimental way that what is equilibrium state. So consider now in these three systems are in equilibrium 2 by 2. Now when system 1 and 2 are in equilibrium, 1 and 2 in equilibrium, so every system has a pressure and a volume. This P2 V2 and P3 V3. When systems 1 and 2 are in equilibrium, so we can find a relation that relates these two quantities into systems. V1 P1, V2 P2. We have a function that put this to 0. The same for system 1 and 3 in equilibrium. So F2 of V1 P1 V3 P3 is 0, and for these two systems in equilibrium, the function of V2 P2 V3 P3 is 0. This function actually doesn't have a complicated or doesn't have an important meaning. Actually, when these are in equilibrium, till now what we know about an ideal gas system are P and V and U. Okay, these are functions of states, and we don't know still temperature. Here with the zeroth law we want to define actually a temperature, and after that the Kelvin temperature we will define in this session. So when till now we know just V and P as quantities of a system. So we here, when we say these are in equilibrium, actually we can find a relation between volume and pressure of this system with volume and pressure of this system. If you think with yourself with this piston displacement, you can actually convince yourself that the equilibrium point of the piston relates to the pressure and volume of these two systems. Okay, from this, as we have done before, we can find P1 as a function of these others is, for example, a function G1 of V1 V2 P2. and here too we have P1. P1 is also another function G2 of V1, V3, P3. Okay? And here we will find another relation that we will use. From here, these two are equal. Okay? G1, a function. Actually, we have a relation between V1, V2, and P2. And this is equal to this one. Another function of V1, V3, and P3. Look at here. We have a relation between these and these are equal. Okay? If we didn't have V1 here, you can see that a function of quantities of system 2 is equal to the same function of quantities, pressure and volume of the other system. So this will be useful if we can remove V1, but we can't do it by ourselves. We should have another relation, which I will explain here. When we have this equality here, actually we have another function of V1, V2, V3, P2, P3. This is another relation between these 5 quantities. But from here, if you actually compare these and these, you can see V1 is not necessary here. V2, P2, V3, P3, V2, P2, V3, P3. Okay? So we can remove V1 here, and this relation is still true. If you actually are obsessive with this, you can put the same function f3 here. So when you remove f1 here, you can remove it here, and the names of the functions are not important. And so we have this, a function, I name it theta 1 of, let me put it 2 because these are 2, theta 2 of V2 and P2 is equal to theta 3 of V3, P3. Let me tell at first that what does the zeroth law tell us? It tells that if systems 1 and 2, each one are in equilibrium with system 3, these two are in equilibrium with each other. But this statement, this law, or this method of actually thinking, I don't know what word to use, is not correct everywhere. For example, imagine you are my friend, and you are friend with another person, but the third person is not friend with me. But here 1 and 3 are friends in equilibrium, actually 2 and 3 are 2, and 1 and 2 are in equilibrium or in a friendship too. This is a zeroth law, but I actually used it in a different way to define a temperature. This theta is a quantity. It is a function, but the function will have actually amount in this point, V2 and P2, and these two. So theta is a new quantity. I define it. Theta is a function of V and P in every system. But this temperature is not the temperature that we know in the ideal gas law, and is not the Kelvin temperature or the Celsius temperature or Fahrenheit, but this is related to that temperatures. Maybe this is T to the power of 2 or anything else. But we have this till here. Now, people actually made a lot of methods to measure temperature, the temperature that we feel it as actually being hot or cool, or cooled or cold, okay? And people invented some methods to measure this quantity that we can feel with our hands, our body, our feelings. And one of these methods was a thermometer that works with gases. Actually, for example, this is the thermometer. Okay, and including a gas, for example, oxygen, nitrogen, or a gas like this, and it can measure its pressure with a method like this. A liquid is in here, and it can compute the pressure of this gas. Okay, and this relation is for any thermometer. X is a quantity, here pressure, but another thermometer may work with the height of liquid. This thermometer works with height as meter of a liquid, and here X will be height, but for this X will be pressure. And why I used this relation? Theta, we actually defined theta as a quantity of temperature, but not that temperature that we know already. And now imagine that X, which thermometer measures that, is alpha, an amount of alpha, a number, multiplied by this theta. Okay, now I want to talk about these gas thermometers. So we have here P equal to alpha theta. Actually, it's better to have some theta 0. It's a line. And experiments show that in low pressures, all thermometers with different gases, for example, this is nitrogen and this is oxygen. When the thermometer works with nitrogen, this line is built, and alpha and theta 0 has amounts, and for oxygen this is held. But when pressure is very low, for every gas these are equal and reach an amount, we want to name this amount of theta the Kelvin temperature, because here pressure of gases are equal and we want to work with this pressure, but because we want to make the ideal gas equation and we should have pressure and temperature and volume with each other. So the line is something like this. If we put theta 0 equal to 273 or something like this, we will have P equal to a constant which is R divided by V to theta, and theta is now T. Okay, remember V is V divided by N, but we use V everywhere. So we have PV equal to RT. But care about this point that this has a circumstance that is correct in low pressures. Okay, this is one property of the ideal gas. An ideal gas has very low pressure. Actually, the particles are not too close to each other, and the particles don't have volume. Actually, the particles are points. And when we say volume of the gas, the ideal gas, we mean the volume of the whole volume, and we don't remove the volume of particles. Okay, so memorize these two properties of the ideal gas, and we have now the relation of ideal gas, and this is a very good progress with us. Now we have defined what is a process. One process that is important is isothermal process. In isothermal process, T is constant. When T is constant, T equal T0, so PV equals constant. PV equals constant. If you want to draw it, plot it, this is a hyperbola. On these points, on every point, the temperature is T0, T0, T0. Now, we want to compute, we want to calculate work here on this diagram, on this process, in isothermal process. W, actually dW, is minus P dV. So W is minus P dV equals, you can put P equal R T0 divided by V. So this will be R T0 integral of dV divided by V from V1 to 2. Okay, now this will become minus r T0 logarithm of V2 divided by V1. This is work in an isothermal process. We have other processes. We have a process that volume is constant and is called sometimes isometric. Imagine a process that volume is constant. For example, this process from here to here. dW is 0 because dW is minus P dV and dV is 0, V is constant. And du, which is dq minus P dV or plus dW, is dq, and we like this because at first let me define heat capacity. Keep it for here. Heat capacity is simple defined, actually is ρ Q divided by ρ alpha. Alpha is a quantity in constant, beta, gamma, and other quantities. Actually, all of the quantities are constant except one, which is alpha. And the notation is this: beta and gamma and others are constant with respect to alpha. If I don't write alpha, I mean temperature. Actually, the heat capacity is important for with respect to temperature. Okay? If I write CV, this will be ρ Q divided by ρ T in constant V. But pressure is not constant. If I tell you heat capacity in constant pressure, this will be ρ Q divided by ρ T in constant pressure. Now, come back here. In isometric, this is isometric process. Here, CV is ρ Q divided by ρ T in constant V, and dQ is equal to du, so actually you can say ρ du is equal to ρ Q2. This will become ρ du divided by ρ T in constant V. So CV, we have this relation. CV is ρ du divided by ρ T when V is constant. And you can calculate the other relation. So U will be CV dt. We have this relation everywhere this is correct. Actually, although we calculated this from the isometric process, but the constant V here actually has in it the concept of isometric process. Actually, this is always correct. Okay? Now, memorize this and let's go to another actually famous process, isobaric. An isobaric process is a process which is done in every point with constant pressure. For example, this process. Pressure is constant, P0. Okay? Let's calculate, for example, Cp here. You can calculate work. This is very easy. dW is minus P dV, and dV is delta V. P is, if you integral, P is constant and it goes out of the integral, and it's easy. Let's calculate Cp. We have Cv here. We want to calculate Cp and see what happens. This is rho Q divided by rho T in constant P. What is dq? dq is du plus P dV, because we had here this by the first law of thermodynamics, and you can have dq as this relation. If you do a partial derivative on both sides of this relation, Cp, which is rho Q divided by rho T in constant pressure, will be rho U divided by rho T constant pressure plus P rho V divided by rho T in constant pressure. If you put U here, Cv is constant and goes out of the derivation, and dt, a partial derivative with respect to t, will be 1, and this will become Cv plus, we can calculate here by the ideal gas relation. Here PV equals RT. P is constant here P is constant, and you want to calculate V is equal to R divided by PT, so rho V divided by rho T in constant pressure, which is this, will be equal to R divided by P. So put R divided by P here. P's will cancel each other, and this will be R. So we have this important relation. This is Cp. This is Cp. So Cp minus Cv is R. This is very important. Memorize these two. Let's go to the other process. We have adiabatic process. Adiabatic process is a process that is done very quickly, and it won't let heat to move out or inside of the system. du is equal to dq minus pdv. In an adiabatic process, dq is 0, and don't think about the experimental concepts. Actually, they can do other things, not just with doing it very quickly. They can have a gas here, and they can put around it something that doesn't let heat to move from it and enter the gas or exit the gas. So this is possible to have this process. So in this process, du is equal to minus p dv. Okay, and we had du. This is du. Oh my god, this is not u. This is du. Okay, and we had du here. Du is these two, so this will be cv dt. We have this for an adiabatic. I wanted to first calculate the relation between V and P in an adiabatic, but I can actually plot it. If this is isothermal, this is adiabatic. Actually, the curve is not hyperbola. This is different. We are going to calculate it here. Let's begin. Minus p dv equals cv dt. What is p? pv equals rt. So v is rt divided by p. So rt dv divided by p is equal to cv dt. So minus r dv on v, we have a cv here, is equal to dt divided by t. What is the answer? The answer is minus r divided by cv logarithm of v is equal to logarithm of t. Actually, it's simpler for me to call logarithm ln. Okay, so ln v to the power of minus r divided by cv is equal to ln t. So v to the power of minus r divided by cv is equal to t. And I don't like actually temperature in diagrams, so I replace it with p. T from the ideal gas relation is pv divided by r. So v to the power of rcv is equal to pv divided by r, and I can write it in this way: p to the power of 1 multiplied by v to the power of 1 plus r on cv is a constant. Actually, it's not r, because when we did the integral, we didn't put a plus c. If we put a plus constant here, and this c would be ln of some constant, and it would be a constant here, and we would have a constant here. This is not r all the time. Okay, what is the power? The power is this. The power here, this is our relation, pv to the power of 1 plus rcv is equal to constant, and the power is cv plus r on cv, which is equal to cp on CV, because if you remember, we calculated a few minutes ago, that Cp minus Cv is R, and this is named gamma. This is a constant, it's named gamma, so P V to the power of gamma is constant, and this is the actual relation of an adiabatic process. Okay, now let's back to the diagram. We calculated the relation, the equation that is that makes the diagram. Here on this curve, PV to the power of gamma is constant. Remember, on an isothermal diagram, this was the curve, and on this T was constant. Here another thing is constant. I don't want to define anything new here in the end of this session, but on this curve the entropy is constant. Okay, and this is the beginning step on defining entropy. Remember that in this process, in adiabatic process, dq is 0 and there's no heat movement actually inside of the system or outside of the system. We don't have heat. When we don't have heat, entropy is constant and delta of entropy is 0. Okay, so remember adiabatic process. So in the next session or after 2 sessions, we will talk about the second law of thermodynamics and we define entropy. Good luck. I hope you enjoy thermodynamics with these videos, and actually just enjoy this lesson.